Welcome to Talk Tensors. It is Friday, February 13th, 2026. I'm your host, and as always, I am joined by our resident expert to decode the papers that built the world we're living in today.
Great to be here. And today, we are doing something a little bit different. Usually, we're looking at the absolute cutting edge, what happened this week in AI.
The latest and greatest.
Exactly. But to really understand the agentic systems we all use now, you have to look at the architectural blueprints. You have to, see where the ideas came from. So we're going back to the archives.
We are. We're rewinding the clock 3 years. We're going back to early 2023. I mean, it feels like a lifetime ago in AI years, doesn't it?
Oh, completely different geologic era. The Wild West, truly.
And we are analyzing a paper that, in my opinion, is one of the most underappreciated architectural breakthroughs of that entire period. It's titled HuggingGPT, Solving AI Tasks with ChatGPT and Its Friends in Hugging Face.
And Its Friends. I always loved that part of the title. It sounds so remarkably wholesome, almost like a children's book.
It does.
But you're right. Make no mistake. This was a heavy piece of systems engineering coming out of Microsoft Research Asia and Zhejiang University. This was not a toy.
No, not at all. Mm-hmm. And the reason we're talking about it today isn't just for nostalgia. It's because this paper proposed a solution to a problem that you could argue still haunts AI development, or at least it completely defined the path we're on now.
The jack of all trades, master of none problem.
Exactly that.
That's a great way to frame it. I mean, if you can put yourself back in the vibe of early 2023, LLMs like ChatGPT and the newly released GPT-4 were just dominating the conversation.
They were everything.
They were. They were these massive, powerful reasoning brains. They could write poetry, they could code, they could pass the bar exam. It was astonishing.
And this is the key. They were trapped. They were stuck inside a text box.
Precisamente. They were disembodied brains. I love that phrase from the paper. Imagine a brilliant mathematician locked in a dark room. You can slide a piece of paper under the door with an equation, and they'll solve it perfectly.
No problem.
But if you ask them, hey, what color is the sky right now? Or please, can you draw me a picture of a cat? They're helpless. They have no eyes, no ears, no hands.
And at the exact same time, outside of that dark room, you had this explosion of activity in the Hugging Face community. You had this massive, chaotic, beautiful library of what I like to call savants.
Right. Models that were hyper-specialized. You had a model that did nothing but detect the edges in a photograph. Another one that only translated English to French.
And that's all it did.
That's all it knew how to do. You had models for depth estimation, for pose detection, for audio transcription, thousands of them.
But these savants, they were.
Well, they were dumb.
In a general reasoning sense, yes, absolutely. A pose detection model doesn't know who the president is. It can't plan a vacation for you. It just knows with incredible precision where your elbows and your knees are in a picture.
So the whole landscape is split. You had the genius brain locked in the dark room, and then you had thousands of skilled specialists wandering around outside with no manager, no one to tell them what to do.
Yeah.
And the industry was really split on how to solve this. One camp, the dominant camp at the time, said, just build a bigger model. Train one giant neural network that can see, hear, speak, and reason all at once.
The God model approach.
The God model. The monolithic approach. And look, that's the path that eventually gave us the massive multimodal models we have today, like Gemini and GPT-4V. It's a valid path.
It's not the only one.
Not at all. And the authors of HuggingGPT, they asked a fundamentally different question. They asked, what if we don't need to retrain the brain to do manual labor? What if we just teach the brain how to be a project manager?
The manager. I love that metaphor for this. Yeah. So instead of doing the heavy lifting itself, the LLM is the one walking around the office, or in this case, the Hugging Face model, hub-tapping specialists on the shoulder.
Yes.
And saying, hey, you're good at edge detection, you handle this, or you're our best text-to-speech engine, it's your turn.
Precisely. And that is the core thesis we're going to explore today. HuggingGPT wasn't a new model, it was a system. It was a wrapper, a framework that turned the entire open source community, all those hundreds of thousands of expert models, into a toolkit for a single chatbot.
It represents that shift from end-to-end modeling, where one neural net does everything, to compositional AI, where an agent assembles a pipeline of tools on the fly to solve a problem.
Which, as you've said before, is how most complex software actually works.
It's rare that one function does everything. You have a database, a front end, a back end, an API layer, all working together.
Exactly. And the aha moment for these researchers was realizing that language, just plain English text, could be the universal adapter, the USB port, to connect all these disparate models together.
Okay, so let's really unpack that. The philosophy of language as a generic interface. How does a text-based chatbot actually, hire a computer vision model? Because on the surface, those are two completely different languages. One speaks in tokens and semantic vectors, the other speaks in pixel arrays and tensors.
This is the absolute key insight. The researchers realized that on Hugging Face, every model comes with a model card.
Right, the little description.
It's basically a resume. It has a name, a description of what it does, maybe some example inputs and outputs, who trained it. All of that is text.
So the LLM just reads the resume.
Essentially, yes, it's that simple and that profound. By feeding these text descriptions into the LLM's prompt, the LLM suddenly understands what tools are in its toolbox.
Okay, that's wild.
And think about the implications. It doesn't need to be retrained to use a new tool. If someone uploads a brand new state-of-the-art depth estimation model to Hugging Face tomorrow,
HuggingGPT can use it
instantly. As long as the description is clear and well-written, the system's capabilities grow with the communities.
That is incredibly flexible. It reminds me of how we learn to use software. I don't need to know how to code a spreadsheet to use Excel. I just need to know which button to click and what the menu says.
That's a perfect analogy.
The LLM is figuring out which buttons to click based on the instruction manual that comes with each tool.
And the advantage here is just massive scalability and modularity.
Yeah.
If you want to add a new capability to a monolithic model, you often have to do a whole new fine-tuning run or wait for the next massive training cycle, which costs millions, maybe tens of millions of dollars.
It's a huge undertaking.
With Hugging GPT, the system gets smarter every single time the community releases a better expert model. It effectively crowdsources its body parts, its eyes, its ears, its hands.
Okay, so that's the high-level philosophy, manager and specialist, brain and body. But the devil is always in the implementation details. Yeah. I want to know how the data actually flows through this thing, because if I tell ChatGPT in early 2023, hey, count the zebras in this picture, it couldn't see the picture. So how does it actually orchestrate this dance?
Right. So the authors break the architecture down into 4 very distinct stages. And honestly, this 4-stage workflow has become the blueprint for almost all agentic systems we see today. If you're building AI agents in 2026, you are likely standing on the shoulders of this architecture. The stages are task planning, model selection, task execution, and response generation.
Okay, let's walk through these one by one. And I really want to get into the weeds on the prompt engineering here, because that feels like the secret sauce. Stage 1, task planning, the brain's blueprint.
This is where all the core intelligence happens. The user sends a request. It might be simple, like translate this, but the system is designed for complexity. Let's use a slightly more complex request from the paper. Describe this image and then read the text aloud.
Okay, so 2 distinct actions there, one depending on the other.
Exactly. The LLM receives this text. Its first job isn't to answer the question. Its first job is to parse that request into a structured plan. The paper specifies that the output at this stage has to be a list of tasks in JSON format.
JSON, the lingua franca of data interchange. Why is that so important? Why not just let the model write a paragraph about what it wants to do?
Because computers need structure. The next stage of the pipeline is code, not an English teacher. A Python script needs to parse that plan. It can't just have the LLM ramble on.
It needs predictable fields.
It needs to know specifically, what is the task type, image to text, for example? What are the arguments, like the file path to the image? And crucially, what are the dependencies?
Dependencies, right? That sounds like project management logic.
It is 100% project management. In your example, describe this image and read the text aloud. The system has to recognize a sequence, a logical flow. You cannot read the text aloud until you have generated the text description.
So task B depends on the output of task A.
Exactly. The LLM has to figure out, okay, task 1, ID task 1, task type image to text, args image.jpg, task 2, ID task 2, task type text to speech, args from task 1. It's building a dependency graph, a directed acyclic graph, or a DAG, if you want to get technical.
And the system then reads that graph to determine the order of operations.
Correct. But here's the catch you alluded to. LLMs in 2023 were notoriously bad at outputting perfect JSON. They were just terrible.
Oh, I remember. They loved to add little conversational intros like, sure, here's the plan you requested. Or they'd miss a comma or forget a closing bracket and the whole thing would crash.
The dreaded JSON syntax error. You'd get a complete failure because the model decided to be polite. It was infuriating.
So how did they solve that? How did they force it to be a reliable machine?
The paper details some really specific and frankly clever prompt engineering. They use what they call specification-based instruction, essentially rigid rules in the prompt like you must respond in JSON format, do not say anything else, your response must start with a...
Just really strict instructions.
Very strict. And also demonstration-based parsing, which is just what we now call few-shot prompting. They show the model examples. Here are 3 examples of complex requests and the correct JSON output. Now do it for this new one, follow this pattern exactly.
This is what we call in-context learning. You're not retraining the model. You're just giving it a pattern to match inside the prompt itself.
Correct. But they did something else, a specific technical detail in the paper that I found fascinating. They mention using logit bias.
Okay, so explain that for the listeners who aren't deep in the weeds of machine learning engineering. What is logit bias?
So under the hood, an LLM predicts the next token, the next word or piece of a word, based on a probability score for every possible token. That score is called a logit. Usually it just picks the token with the highest score.
The most likely next word.
Right. Logit bias is a parameter in the API that allows the engineer to manually reach in and force the probability of certain tokens up or down. You can just put your thumb on the scale.
So they literally gave the model a cheat sheet.
Exactly. The researchers set the logit bias to 0.2 for the curly brace characters. They basically told the model, I don't care what you think the most poetic opening to the sentence is. I am statistically forcing you to start this output with a curly brace.
That is hilarious. It's such a clever hack. But it works. It forces the model into code mode immediately.
It does. And they also set the temperature parameter to 0.
Which makes perfect sense. For the planning phase, you want zero creativity. You want pure deterministic logic. You want the same input to produce the exact same plan every single time.
Exactly. You save the high temperature for writing poetry, not for orchestrating API calls. You need reliability above all else. The plan can't be creative.
Okay, so stage 1 is the brain making a very structured, very logical to-do list. It says we need an image classifier, then we need an object detector, then we need a text-to-speech engine. But it hasn't picked which specific models to use yet, right? It just knows the types of jobs that need doing.
Correct. And that's a crucial distinction. It has defined the roles, but it hasn't cast the actors yet. That brings us to stage 2, model selection, the hiring phase.
This is the part that, even now, kind of blows my mind a little bit. Hugging Face has hundreds of thousands of models. I mean, millions now. You can't fit 100,000 model descriptions into the context window of ChatGPT. You'd run out of tokens instantly.
No, not even close. You'd crash the API. So they use a multi-step filtering mechanism. First, they filter by the task type that was identified back in stage 1. If the plan calls for object detection, they immediately ignore all the translation models, all the audio models, all the text generation models.
That narrows the field considerably.
It does. But you're right, there are still probably 5,000 object detection models on the hub, so that's still too many.
So what's the next filter?
So then they rank them. And they use a metric that is incredibly simple, but also incredibly pragmatic, popularity. They just look at the number of downloads on Hugging Face.
The wisdom of the crowds. If everyone is downloading and using Facebook Desktop ResNet 101, it's probably decent. It probably works.
It's a bit of a brutal heuristic, but it's efficient. And it's a great way to avoid the system picking some obscure, broken model that a student uploaded for a homework assignment 5 years ago and never touched again.
A good proxy for quality.
A very good proxy. So they take the top K candidates, let's say the top 10 most popular models for that task, and they feed only those specific model descriptions into the LLM in a new prompt.
So it's a dynamic prompt. The prompt is constructed on the fly. Dear manager, for the object detection job, here are the top 10 candidates. Here are their resumes. Please read them and pick the best one for this specific situation.
Yes, and this is called in-context task model assignment. And the LLM can now apply its reasoning to the nuances. Maybe one model's description says it's better for indoor scenes, and another says it's trained on wildlife. If the user's original prompt mentioned zebras on the savannah, the LLM can make an intelligent choice.
So the manager actually reviews the resumes and makes a final hiring decision on the spot. You're hired.
Correct. And it does this for every single subtask in the plan. It's a series of micro decisions.
Okay, so the plan is set. Our team of specialists is hired. Now we actually have to do the work. Stage 3, task execution.
This is where the system stops being just a chatbot and starts actually computing. The system's control script invokes the selected models. Now, the paper discusses a really interesting infrastructure detail here: hybrid endpoints.
Hybrid usually means a mix of local and cloud, right?
Exactly. The authors knew that relying entirely on the Hugging Face inference API, the cloud could be slow or, hit rate limits or just be down. So their system allows for local endpoints. If you have the model downloaded on your own machine or on the server running HuggingGPT, it will prefer to use that.
That's smart. It optimizes for latency and reliability.
Absolutely. But it also optimizes for time in another really clever way: parallelism. Remember that dependency graph from stage 1?
Right, the DAG that shows which task depends on which.
So if the plan says describe the image and a separate independent task is count the objects in the image, those two tasks don't depend on each other. You can do them at the same time.
They can run in parallel.
And HuggingGPT is smart enough to identify these non-dependent tasks on the graph and execute them simultaneously. It spins up 2 different processes.
So it's multitasking. While one part of the system is writing a caption, another part is drawing bounding boxes around the objects.
Exactly. This speeds up the total inference time significantly, which is crucial because, as we'll discuss, chaining multiple models together can get very slow, very fast. Any parallelization you can find is a huge win.
Okay, so the specialists have all done their work. We have a text file with a caption, a JSON file with a list of objects and their coordinates. Maybe we have an audio file that was generated. But the user doesn't want a zip file of random outputs. They want a coherent answer.
Which leads us finally to stage 4, response generation, the manager's report.
The manager gathers everyone back in the conference room to get their status updates.
A perfect way to put it. The central LLM receives all the raw outputs from the various tools. It gets the text from the captioning model, the bounding box coordinates from the detection model, the file path of the generated audio from the text-to-speech model, and it has one final specific prompt. Summarize all of this.
It has to synthesize it all into natural language.
It does. And the prompt explicitly instructs the LLM to speak in the first person. I have processed the image and found 3 zebras in a tree, or here's the audio file you asked me to create. It's designed to create the illusion of a single cohesive intelligence, even though a dozen different neural networks might have contributed to the final answer.
And the paper mentions something important about reliability here too, right? What happens if a tool fails?
Yes, this is a key safety feature. If a model fails, say the image generation API times out or returns an error, the execution log reflects that failure. That log is passed to the LLM in this final stage, and the LLM is instructed to report the failure honestly.
So it won't just make something up.
Exactly. It will say something like, I tried to generate the image you requested, but the tool I used encountered an error. This is crucial to avoid hallucination, where the LLM might just make up a description of an image that was never even generated. It maintains trust.
That is a critical safety and reliability feature. So that's the loop. Plan, hire, execute, report. It sounds so elegant in theory, but did it actually work? I mean, there's a famous example from the paper that went viral, the reading girl example.
Oh, yeah.
I feel like this was the moment that made everyone really get it. Can we visualize that for the listeners?
Oh, this is the canonical example. It's the one that made everyone in the field sit up and pay attention because it showed off the compositional nature of the system so perfectly. The user request was incredibly complex for the time.
What was it?
It said, please generate an image where a girl is reading a book and her pose is the same as the boy in the example, .jpg, then describe the new image.
Wow. Okay, just let's unpack that. That is an absolute nightmare for a standard monolithic models from 2023. You have an input image, the one with the boy. You have a condition, the same pose. You have a generative task, a girl reading a book. And then you have a descriptive task, describe the result.
Exactly. It's a multimodal, multi-step reasoning problem. And HuggingGPT nailed it. Let's trace the workflow step by step.
Okay, let's do it.
First, task planning. The LLM breaks it down. It identifies that it first needs to understand the pose from example.jpg. So, in the execution stage, it doesn't just look at the boy's image. It hires a pose detection model, something like OpenPose. This model's only job is to analyze the image and output a skeletal structure, just the coordinates of the joints. It strips away the boy, the background, everything, and just keeps the stick figure.
Okay, so the output of the first tool is just that pose data, a skeleton.
Correct, a JSON file with key points. Then the system moves to the next task. It needs to generate an image. It selects a pose-to-image model. This is where something like ControlNet comes in. The LLM instructs the ControlNet model, take this pose data as your control signal and generate a new image based on the text prompt, a girl reading a book.
This is the aha moment for me. This is the magic trick. It passed the output of one specialized tool, the pose detector, as the input into a completely different specialized tool, the image generator. That is true chaining.
It is. Most agentic systems before this were just question, tool, answer. This was tool, tool, tool. It was a true pipeline. But it doesn't stop there. The plan wasn't finished.
Right. It still had to describe the new image.
After generating the image of the girl, the system then ran an object detection model on the newly created image to identify the objects within it. Then it ran an image captioning model to generate a natural language description. Finally, some versions of this demo even ran a text-to-speech model to read that final caption out loud.
So from one single sentence from a user, it spun up a pipeline of, 5 or 6 different independent AI models?
Let's count them. Pose detection, post-image, object detection, image captioning, maybe text-to-speech. 5 models, minimum. All coordinated by ChatGPT without a single line of custom code written by the user.
That is just wild. It really turns the LLM into a kind of real-time software engineer that writes code using other models as its functions.
And it wasn't just vision. The paper highlights all sorts of examples: text-to-video generation, audio-to-text summarization. They showed it doing complex visual question answering. They really leaned into the multimodal aspect to show off that the system could handle any modality as long as a model for it existed on Hugging Face.
It makes you realize how powerful the tool use paradigm is. But we have to be critical. They built this thing, they have the fantastic reading girl demo, but did they actually measure if it was any good? Or was it just a really cool cherry-picked demo?
They did do quantitative evaluation, which I really appreciate. They didn't just rely on vibes. They specifically designed a benchmark to test the planning capability.
The brain.
They wanted to know how good the brain was. So they compared GPT 3.5, the newly released GPT-4, and some of the top open source models available at the time, like Alpaca and Vicuna.
And I'm guessing the brain mattered.
Hugely. It was night and day. GPT-4 significantly outperformed all the others, especially on what they called graph tasks. These are the complex requests with multiple dependencies, like the reading girl example.
And the smaller models.
The smaller open source models, like Alpaca 7b, really struggled. They would often fail to produce valid JSON, even with the logit bias hacks and the few-shot examples. Or, more subtly, they would mess up the logical order. They might try to read the text aloud before it was ever generated from the image. They couldn't reason about the dependencies correctly.
This just validates the whole brain versus body thesis, doesn't it? The body can be made of specialized, relatively simple tools, but the brain needs to be high IQ. You need a really smart manager to coordinate all the specialists.
Exactly. If the project manager is confused, the best team of specialists in the world can't save the project from chaos. They also did a qualitative comparison to other agent frameworks that were getting a lot of hype at the time, like AutoGPT and Baby AGI.
Oh, right. AutoGPT. That was the one that everyone was running on their laptops for a week, trying to get it to order a pizza. And it would end up getting stuck in a loop, searching the web for the history of pepperoni for 3 hours.
The infinite loop problem. That's because AutoGPT used iterative planning. It would take one step, look at the result, and then plan the very next step. It's great for open-ended exploration, like research a topic, but it's very prone to getting lost or sidetracked.
It didn't have a map.
It was trying to draw the map as it walked. HuggingGPT, on the other hand, used global planning. It plans the entire DAG, the entire roadmap up front. It says, here are the 7 steps we're going to take in this order. Now execute.
It measures twice, cuts once.
Ideally. The paper argues that for specific AI tasks where the tools are well-defined, this global planning approach is much more stable and reliable than the iterative figure-it-out-as-you-go approach.
And they did human evaluation on this too, right?
They did. They had human experts rate the passing rate and rationality of the plans generated by the different models. And again, GPT-4 achieved very high scores, confirming that the bottleneck really was the controller's intelligence. When the controller was smart, the system worked beautifully. When it wasn't, the whole thing fell apart.
Okay, we've phrased it enough. Nothing is perfect, especially not a research prototype from 2023. What broke? What were the limitations they ran into?
The authors were quite honest about the bottlenecks in the paper. The biggest one, by far, was latency. Speed. Think about that reading girl example again. You are making an API call to OpenAI for the planning stage. Then another API call for the model selection stage. Then you have to execute 5 or 6 sequential model inference calls, some of which, like image generation, can take many seconds. Then another final API call for the summarization.
This isn't a real-time chat. You could be waiting 30, maybe 60 seconds for a response.
Easily. And that kills the conversational vibe. If a user asks a question and the chatbot says, hold on, let me think for a minute, they're going to get frustrated and leave.
Totally. What else?
Another major issue is context limits. Even with their clever filtering mechanism, you can only describe so many models in the prompt for the selection stage. If Hugging Face has 1 million models and you filter down to the 10 most popular candidates, you might still miss the absolute best one for the job if it happens to be the 11th most popular. Your filter isn't perfect.
And reliability must have been an issue.
It's the house of cards problem. It's a brittle system. If the LLM makes a single syntax error in that initial JSON plan, the whole chain breaks. Or if just one model in the pipeline errors out, if the pose detector fails to find a person in the image, it passes garbage to the next step and the whole request fails.
And I have to imagine cost was a factor. Running a GPT-4 call plus 6 different expert models on probably GPU instances for every single user query. That is not cheap.
Definitely not. An end-to-end multimodal model is almost always going to be more efficient because it shares weights and parameters. Here, you are loading entirely different, sometimes massive neural networks into memory for each step. It's computationally very, very expensive.
But despite the cost and the slowness and the brittleness, it was a profound proof of concept. It showed that AI doesn't have to be a monolith.
It absolutely paved the way for what we now call tool use or function calling in all the major commercial APIs. When OpenAI released their functions feature later that year, it was essentially them productizing the planning stage of HuggingGPT. They baked the ability to output structured JSON calls directly into the model's training.
So HuggingGPT was the research prototype for the agentic future that we're all living in now. It shifted the entire mindset of the field from what can this model do to what can this model manage?
I love that phrasing. What can this model manage? It brings up a really interesting philosophical point about the direction AI development is taking. On one hand, you still have the God models trying to internalize every possible skill. On the other hand, you have this agentic approach where the model is more of a router, a coordinator.
And the question is, which side is winning?
It feels like a convergence, doesn't it? The brain is getting sharper and more capable on its own, but it's also getting much better hands and tools to work with.
Exactly. The brain is getting better hands.
That's a great way to put it.
Okay, we've dissected the paper. We understand the architecture, the wins, the failures. Now, it's time for my favorite part of the show. I want to take these core ideas and push them off a cliff. I want to see where they land.
Let's do it. Time to get speculative.
It is time for Novel Notions.
Laughs. I always get a little nervous during this part. I feel like we're going to get angry emails from researchers.
That's fine. Disclaimer. The following segment is for entertainment purposes only. These ideas are speculative extrapolations based on the paper's architecture. We are just two people talking into microphones. We are not financial advisors or prophets.
Though we have been right before, just saying.
We have. Okay, I'll go first. Idea number 1. The paper talks about language as interface. The LLM selects an existing model from the hub. But what happens when the LLM looks through Hugging Face and says, none of these tools are good enough for this weirdly specific task?
Okay, long tail problem.
Exactly. I'm calling this the JIT train agent just-in-time training.
Oh, I like where this is going. So instead of just hiring a specialist, the manager trains a new specialist on the spot.
Exactly. The planning stage identifies a gap. It says the user wants to detect glitches in 1990s VHS tapes. There is no pre-trained model for that. So the execution stage doesn't just call an API. It spins up a web scraping tool, goes to Google Images, finds 50 examples of VHS glitches, it downloads them, maybe does some basic cropping.
It curates its own microdata set.
Yes. Then it spins up a training loop. It takes a base model, like a standard Lana Vision adapter, and runs a LoRa, a low-rank adaptation, a fine-tuning on the fly.
Wow. So it creates a temporary disposable expert model that exists only to solve that one user request.
Yes. Takes maybe 5 or 10 minutes to train. It trains the new LoRa, runs the inference to answer the user's question, and then it can just delete the model weights. a one-time use tool.
That is actually plausible. We already have languages interface. This would be languages trainer. You're automating the role of the machine learning engineer. The LLM is writing the training script, curating the data set, and maybe even evaluating the loss curve to see if the training is working.
And because it's using LoRa's or other lightweight adapters, it's not retraining the whole brain. It's just learning a tiny, very specific new skill for 10 minutes.
This totally solves the long tail problem. Hugging Face has a lot of models, but it doesn't have a model for everything. A JIT train agent builds the tool it needs when it needs it.
It's the ultimate MacGyver AI. It builds the tool out of whatever it can find on the internet.
Okay, that's a good one. I've got one. My issue with the original HuggingGPT is that it picks the one best model based on download count. That feels rudimentary. It's a bit like hiring the person with the most Twitter followers. It's not always the best signal.
It's a blunt instrument.
It is. So I'm proposing the Darwinian model arena.
Go on, tell me more.
Instead of the LLM selecting one model, the agent selects, say, the top 5 competing models for the same task. It instantiates what I'm calling the Council of Rivals. It then runs all 5 models on the user's input in parallel. So 5 different object detectors all try to find the zebras in the image.
A bake-off, a blind taste test.
Exactly.
Yeah.
Then, and this is the key, a separate sandbox judge, LLM, blindly compares the 5 outputs. It doesn't know which model produced which result. It just looks at the quality.
And it picks a winner.
It picks a winner. It says, Model C found the zebra that was partially hiding behind the bush while the others missed it. Model C wins this round. But here's the kicker. The system then updates the model description, or a metadata database. It adds a note to Model C's internal resume, confirmed high performance on occluded animals, and it might add a negative note to Model A's.
So the system is self-optimizing its own selection process. It's building a reputation system that isn't based on human likes or download counts, but on actual empirical performance in the field?
Precisely. Over time, you build a Darwinian hierarchy of tools. The system learns which tools actually work best for which specific subtasks, regardless of what their marketing copy says. It creates an evolving ecosystem of experts where the best tools rise to the top through competition.
That is incredibly powerful. It's like an adaptive immune system that learns which antibodies work best against which specific pathogens through experience.
And it solves the reliability issue too. If one model fails or errors out, you have 4 backups running in parallel. The user still gets an answer.
I love that. The JIT train agent and the Darwinian model arena. 2 different but complementary paths forward from the original HuggingGPT. One focuses on creation, the other on selection and refinement.
And honestly, if you look at the trajectory of AI since this paper came out, we're seeing elements of both of these ideas starting to emerge. We see automated fine-tuning services, and we see things like mixture of experts architectures, which are basically a hard-coded version of that arena, routing queries to different submodels.
It all comes back to that core insight from the paper. No single model can be the master of everything. Intelligence, whether human or artificial, is compositional. It's about coordination.
We don't need bigger models. We just need better coordinators.
I think that's the lasting legacy of HuggingGPT. It wasn't the smartest model in the room, but it was the one that knew who to call for help.
And in a world of infinite information and specialized skills, knowing who to call is perhaps the most valuable skill of all.
I think you're right.
Indeed. That wraps up our deep dive into HuggingGPT. Please check the show notes for the link to the original paper, Solving AI Tasks with ChatGPT and its Friends in Hugging Face. It's a classic read and surprisingly accessible.
It really is. Definitely worth your time.
Until next time, keep your tensors flowing.